Good morning, dear students. In the previous lecture, we have gone through the concept of stack and queue. In this lecture, our focus will be on various searching and sorting techniques. We have various searching techniques like linear search, binary search, and Fibonacci search. Along with those searching techniques, also we are having various sorting technique named as selection sort, bubble sort, insertion sort, quicksort, merge sort, heap sort, radix sort. In this lecture, we will discuss few searching techniques and various sorting techniques. Also, we will discuss several examples, algorithm. Along with algorithm, we will see time required for each technique. So, first technique is linear search. Then we will discuss examples for linear search, pseudocode for linear search, then time complexity, then we will see what do you mean by binary search, how binary search overcome drawback of linear search. We will see several example, algorithm, and then time complexity. Linear search, as name suggests, we are having an array of n elements. Also, we are having a key element. What do you mean by key element? Key element is an element that we are going to find in array. That is, if key is present, we print as key is present. If it is not present, we print it as absent. So, technique behind linear search is, first we accept an array of n elements. We store those n elements into the array. We accept key element, and once we accept key element, we compare key element starting from the 0th index with each and every element in the array till it is found. Once again I repeat, in linear search, first we accept array elements, we store those array elements into the array, we accept key element. Once we accept key element, we compare key linearly, sequentially with each and every element starting from 0th index till it is found. But if key is absent, at that time we require unnecessary comparison. For example, if you consider this example, there is array A of size 5 and elements inside array are 3, which is stored at 0th index, then 2 at first index, minus 3, 10 and minus 5. And suppose key is minus 3. Once we accept key, we compare key minus 3 with a of 0, that is 3. It is not matching. Again we compare key with next element, that is with a of 1, 2. Again it is not matching. Again we compare key element with next, that is a of 2. Yes, key is minus 3, a of 2 is minus 3. Here we print yes, key is found. Suppose I replace key as 9. See what happens. 9 is compared with a of 0, it is not matching. Then a of 1, again not matching. A of 2, a of 3, a of 4. Oh my god, key is not matching at all with each element. So in this case we print key as absent. So basically technique is we compare key element with each and every element with each and every element inside array till it is found. Once it is found, we print as key is found. Otherwise, if it is not, we print key is absent. Advantage of linear search technique is, this technique is quite simple. We have to do nothing, just we have to do comparison of key element with each and every index. But drawback is that this technique require too much time, because if we have an array which is having size very large, and suppose that key that we are going to find is absent, at that time we have to make so many comparison which are totally best. So this is the drawback of linear search. Once again I repeat, if size of array is large and the key that we are going to find is absent, at that time we require so many comparisons. We will see how this drawback is get overcome by binary search. Now we will discuss algorithm. uh, this is the algorithm for linear search. uh, Here we have considered an array A of size n, and we have stored element that we are going to find in variable key. So suppose consider this example, key is minus 3. Initially I is equal to 0. In this case the value of n is 5. 0 is less than 5. Yes, it is less than 5. First, minus 3 is compared with a of 0. No, it is not equal to. We do not enter inside. If I get incremented, I becomes 1. 1 less than 3. Yes, key is compared with a of 1. Again key is minus 3, a of 1 is 2. It is not matching. Again I plus plus, I becomes 2. 2 less than 3. If key equal to a of 2, yes, key is minus 3, a of 2 is minus 3. Condition is true. We print key as present. Break, we come out from the for loop. If I equal to n, of course not. That is, we do not print key as absent, and we come out from the function. But suppose I replace key element as 9. In this case key is compared with a of 0, a of 1, a of 2, a of 3, a of 4. When I becomes 4, key is compared with a of 4, a of 4 is minus 5, key is 9. Again it is not equal, again I plus plus, now I get incremented, it becomes 5. 5 is less than n, that is 5. Condition is false, we come out from the for loop. If I equal to n, but value of I and n both are equal, that is, here we get a message key as absent. So in this way this linear search works. Now we will discuss time complexity of linear search. If we calculate frequency count I equal to 0, the statement get executed exactly once. I less than n, this statement get executed n plus 1 times. I plus plus get executed n times, and body inside for loop get executed n times. That is, here we get a polynomial of degree 1. In the other words, body within for loop get executed n times, therefore time complexity of linear search is big of n. As we already have discussed, drawback of linear search. Drawback of linear search is, if size of array is large, at that time we require so many comparisons. The drawback of linear search is get overcome by the another searching technique, which is binary search. Actually binary search technique belongs to divide and conquer strategy, where we divide the problem into sub problems, we find sub solutions, and finally we merge all sub solutions to get final solution. Binary search belongs to divide and conquer strategy. How? See what is the technique. In binary search we have to manage three things: low, high and mid. Suppose we consider same array -5, -3, 2, 3, 10, and suppose key is -3. So basic technique of binary search is, in the first iteration we have to set low, high and mid. Initially we set low at 0th index, high at n-1th index. Here high value is 4. We check the value of low is less than or equal to high. If this is so, we calculate mid. Once we calculate mid, we compare key with a of mid. If it is equal, we directly print message as key is present. If it is not equal, there are two possibilities. Key may be larger than that of mid element. If this is so, we have to update value of low as it is equal to mid plus 1, high it remains as it is. And if key value is smaller than that of mid, at that time we have to reset value of high, it is equal to mid minus 1. In this case low becomes as it is. Once again I repeat, in the first iteration we set low at 0th index, high at n-1th index. We check whether value of low is less than or equal to high. If this is so, we calculate mid. Mid is equal to low plus high divided by 2. Once we calculate mid, we compare key with a of mid. If it is equal, we print as key is present. But if it is not equal, there are two possibilities. Key may be larger than that of mid element. If it is larger, at that time we update low as it is equal to mid plus 1, high remains as it is. And if key is smaller than that of mid element, at that time low it becomes as it is, and we replace high as it is equal to mid minus 1. And we continue this procedure till key is found. Each time we have to check the condition low is less than or equal to high. But if once low is greater than high, definitely we can say key is absent. So let us see example. In example, key is minus 3. So in first iteration I set low, it is equal to 0. High, I have set it to last index 4. Low is less than or equal to high. Yes, I calculate mid, it is equal to 0 plus 4 divided by 2, and it is equal to 2. I compare now minus 3 with a of mid, that is a of 2. A of 2 is 2, that is key is minus 3. In this case, key value is less than a of mid, that is definitely our key is situated at the left hand side of the mid element. Therefore we set high to mid minus 1, and low it becomes as it is, therefore low equal to 0 as it is, and we reset high as mid minus 1. Current mid value is 2, 2 minus 1, it is equal to 1. Again we check low value is less than or equal to high. Yes, if this is so, as usual we calculate mid, it is equal to 0 plus 1 divided by 2, it is equal to 0. Mid value is 0. We compare key, that is minus 3, with a of 0. A of 0 is minus 5, key is minus 3, key is greater, therefore uh, we now key is greater, therefore uh, we reset value of low, it is equal to mid plus 1, and in this case high becomes as it is, that is low is equal to 0 plus 1, and high it is equal to, it becomes as it is 1. We check whether low is less than or equal to high. Yes, 1 is less than or equal to 1. We calculate mid, mid is equal to 1 plus 1 divided by 2, that is it is equal to 1. Now mid is 1. We compare key, that is minus 3, with a of 1. A of 1 is minus 3. Yes, both are equal, therefore here we print key is present. In this way binary search work. The entire technique is, first we set low at 0th index in the first iteration and high at last index. We check whether low is, the value of low is less than or equal to high. If this is so, we calculate mid. Once we calculate mid, we compare key with a of mid. If it is equal, directly we can print yes, key is present. Otherwise, if it is not equal, we check whether key is smaller or greater than that of mid element. If it is smaller than that of mid element, at that time low becomes as it is, and we replace high, it is equal to mid minus 1. If key is greater than that of mid element, at that time we replace low equal to mid plus 1, high it becomes as it is, and every time we check low value should be less than or equal to high. Once low is greater than high, definitely we can say key is absent. So let us discuss algorithm for binary search. Yeah, I we recently have seen an example array. In algorithm we have considered array of size n and number that we are going to find I have stored it in variable key. Here I have set low it is equal to 0, high it is equal to last index, that is n minus 1. I have declared mid. So I have used do while loop. Do we calculate the value of mid. Once we calculate value of mid, we compare key with a of mid. If it is equal, we print as key is present, and directly break statement get executed. And once break statement get executed, we come out from do while loop. At that time, uh, if low is greater than high, condition is definitely false. So we do not get message key as absent. But suppose key is not equal to a of m at that time, else if we check whether key is greater than a of m. If this is so, at that time we update low it is equal to mid plus 1. Otherwise, if this also condition is not true, by default else block get executed. Why this is so? Because key is not equal to a of mid. First situation we have checked. Second situation, key is not greater than that a of mid, that is key is smaller than that a of mid. Therefore we update high it is equal to as m minus 1. So we continue this procedure till low is less than or equal to high. Once low is greater than high, we come out from do while loop. Once we come out from do while loop, we check if low is greater than high. Yes, this is so. We print key as absent. For example, if we solve above example, at that time, what happens? Initially low equal to 0, high equal to 4, key equal to minus 3. We enter in do loop. We calculate mid. It is equal to 0 plus 4 divided by 2, and it is equal to 2. We compare key with a of 2. It is not equal. Key is minus 3, a of 2 is 2, that is key is less. Therefore we update value high, it is equal to mid minus 1, that is we get high as 1. High value now is 1. We check low is less than or equal to high. Yes, 0 is less than or equal to high. Again we calculate mid. It is equal to 0 plus 1 divided by 2, and it is equal to 0. Now key is minus 3 is compared with a of 0. Again it is not equal. In this case, key value, that is minus 3, is greater than a of 0. Therefore low value get updated. It is equal to mid plus 1, and now it becomes 0 plus 1, that is 1. Low is less than or equal to high. Low value is 1, high value is 1, both are equal. Again we calculate mid. 1 plus 1 divided by 2, it is equal to 1. Key is compared with a of 1. A of 1, yes, minus 3. A of 1 is minus 3, key is minus 3, that is we can say key is present. Break, we come out from do while loop. At that time following condition is false. In this way we get key as present. So this is how binary search work. Now we will discuss time complexity of binary search. I already have told binary search belongs to divide and conquer strategy, where we have problem of size n. We divide that problem into subproblems and so on. Initially we have problem of size n. We divide it into two equal parts, n by 2, n by 2. Again n by 2 is further divided into n by 4, n by 4, so on. If we calculate tree, the height of tree becomes log n. Therefore the time complexity of binary search is log n. In this way, binary search requires minimum time than linear search. Sorting technique. I already have told we are having various sorting technique. Out of them, first sorting technique is selection sort. First, I will explain how selection sort works. If we have an array of size n, then we require at max n minus 1 passes to sort the entire array. Once again I repeat, if we have an array of size n, we require at max n minus 1 passes to sort entire array. In the first pass, a of zeroth element is compared with rest of all. Whenever previous number is larger than that of next, we swap those elements. In second pass, we compare a of first element with remaining all. In third pass, we compare a of second element with rest of all, and in this way we continue the procedure. Once again I repeat, in the first pass, element at a of 0 is compared with rest of all. In the second pass, element at a of 1 is compared with rest of all. In the third pass, element at a of 2 is compared with rest of all, and so on. In this way, suppose this is the array which we have given 3, 2, minus 3, 10, minus 5. First 3 is compared with 2. Previous number is larger, therefore we swap our array. It becomes 2, 3, minus 3, 10, minus 5. Again 2 is compared with minus 3. Again we swap them. Again minus 3 is compared with 10. No need to swap. Again minus 3 is compared with minus 5. So this is the output of pass 1. In the second pass, a of 1, that is 3, is compared with 2. We swap it. Again 2 is compared with 10. 2 is compared with minus 3. In next pass, 3 is compared with 10. Then 3 is compared with 2. And we get output in the third pass only. In this way, this selection sort works. Once again I repeat, in selection sort, if we have an array A of size n, at that time we require at max n minus 1 passes to sort the entire array. In the first pass, element at a of 0 is compared with rest of all. In the second pass, element at a of 1 is compared with rest of all. In the third pass, element at a of 2 is compared with rest of all, and so on. Let us see the algorithm for selection sort. This is the algorithm for selection sort. If we analyze this selection sort, at that time we are having for loop within for loop. Inner for loop get executed n times, outer for loop get executed n minus 1 time. If we calculate the frequency count of entire algorithm, we get polynomial which is of order 2. Therefore, time complexity of selection sort is big O n squared. Then we will see next sorting technique as Bubble sort. In bubble sort, if we are having an array of size n, here also we require at max n minus 1 passes to sort entire array, and in each pass a of 0 element is compared with a of 1, a of 1 element compared with a of second element is compared with a of third element is compared with a of fourth, and so on. So difference between bubble sort and selection sort is, in selection sort, in the first pass element at a of 0 is compared with rest of all. In the second pass element at a of 1 is compared with rest of all. In the third pass element at a of 2 is compared with rest of all, and in the last pass element at n minus 2 index is compared with element at n minus 1 index. But in bubble sort, in each pass, if we are having n elements, we require n minus 1 passes at max, and in each pass element at a of 0 is compared with element at a of 1, element at a of 1 is compared with element at a of 2, element at a of 2 is compared with element at a of 3, till element at a of n minus 2 is compared with element at a of n minus 1. That is, element is compared with its adjacent element. For example, if we consider array like 3, 2, minus 3, 10, minus 5, in the first pass 3 is compared with 2, we need to swap, again 3 is compared with minus 3, we need to swap, again 3 is compared with 10, no need to swap, 10 is compared with minus 5, we need to swap. Okay, similarly, if we apply passes, such passes, n minus 1 passes, definitely we get an array in the sorted order. So this is output. Now we will see algorithm for bubble sort. Yes, here we have made comparison of each element with its adjacent element, and again if we compute frequency count of this algorithm, we get a polynomial of order 2 definitely. Therefore time complexity of bubble sort is also big of n squared. That is, selection sort, bubble sort, both are having time complexity as big of n squared. Again we are having one more sorting technique as which is named as Quicksort, which is the most fastest sorting technique. Why it is known as Quicksort? Because it is the fastest sorting technique, means it requires minimum time to execute. It requires minimum time to sort entire array. Again, Quicksort technique belongs to divide and conquer strategy, means we are dividing the problem of size n into sub problems. Again, sub problem is divided into further sub problems, and so on, and finally we are finding sub solutions, and we merge all those sub solutions in order to get final solution. First I will explain technique for Quicksort. The technique is quite simple. element at a of 0 is considered as pivot. Then we set I index, we set I to index 1, we set j to index n minus 1. Once again I repeat, a of 0th element is considered as pivot. We set I to 1 index, we set j to n minus 1 index. We compare a of I with pivot. If it is greater, we increment I. Again, a of ith element is compared with pivot. If it is, we once we set pivot ij, we compare a of ith element with pivot element. If it is smaller, we have to increment value of I. Again, we have to compare a of I with pivot. If a of I is smaller, we have to increment value of I. But if a of ith value is greater than that of pivot, I get stopped, and we compare a of j. A of j, if a of j is greater than pivot, we decrement value of j. Again, we compare a of j with pivot. If it is greater, we decrement j. But if a of j is smaller than that of pivot, we stop j. I is stopped, j is stopped. We check if I is less than j. If this is so, we compare a of I and a of j, and we continue. That is a of I. We check whether a of I is smaller. If this is so, I plus plus, I plus plus. If it is not, I get stopped. And when I get stopped, we check a of j. If it is greater than that of pivot, j get decremented, and so on. We continue this procedure till I is less than j. Once I is greater than j, we make swapping of a of j and pivot. Now pivot element comes at that jth index, and once we get pivot element, our list is divided into two sublists. That is, first sublist is situated at the left hand side of pivot, and second sublist is situated at right hand side of the pivot. And same technique we apply at left hand side, and same technique we apply at right hand side. At left hand side, again we get pivot. In this way, we continue the same procedure at the left sublist as well as for the right sublist, and finally we merge all sub solutions to get final solution. For example, consider this example. We set pivot at a of 0, that is 7 is the pivot element. We set I to index 1, we set j to index 6. We compare whether a of I, that is 2, is it smaller than 7? Yes, I plus plus, I is at index 2. A of I, that is 1, is smaller than 7. I plus plus, I get incremented. Now I becomes 3. A of I 5. Again it is smaller. I plus plus, I becomes 4. Again a of 4, that is 11. Now it is not smaller. I stopped at index 4. I stopped. Now we start from j. A of j, that is 9. Is it greater than pivot? Yes. J minus minus, j becomes 5. Again we check whether a of j, that is 4, is it greater than 7? No. Now, j is stopped. I is stopped, j is stopped. I is 4, j is 5. That is, I is at index 4, j is at index 5. That is, I is less than j. Therefore, we swap a of I and a of j. That is, a of I is 11, a of j is 4. We make swapping, and once we swap, a of I and a of j array, it becomes like this. Okay, again, after swapping a of I, a of j, we continue the procedure, that is we check a of I, that is 4, is it less than pivot? Yes. I plus plus I is 5. Again we check a of I, that is a of 5 11, is it smaller? No. Now I stopped at index 5, and we once I stop we check a of j, that is 11, is it greater? Yes. J minus minus, now j value is decremented, j is at index 4, but once j is at index 4, I value is greater than j, because I is 5, j is 4. I already have told, once I is greater than j, we make the swapping of a of j and pivot, that is we make the swapping of 7 and 4. The element at a of j is now 7, and this is the pivot element. Once we get pivot element, our list is divided into two parts: left sublist, which is uh, situated at the left hand side of 7, right sublist, which is situated at the right hand side of 7. And for left sublist we repeat the above mentioned procedure. Similarly, for right sublist we repeat above mentioned procedure. At every step we get new pivot, new sublist, we continue above mentioned process, and finally we get um, final solution, which is our sorted array algorithm. This one be the algorithm for quicksort. The same procedure, just I have mentioned, if a of I is less than or equal to pivot, I plus plus, if a of j is greater than pivot, j minus minus. If I is less than j, we make the swapping of them. Once I is greater than j, we make swapping of pivot and a of j. In this way, here we are performing the partition, and once we perform partition, we are dividing list into two sublists, and we are giving recursive call for quicksort from 0th index to j minus 1th index, and second recursive function from j plus 1 index to last index. In this way, if we make the analysis of quicksort, again we have problem of size n. We are dividing it into subproblems, subproblems, subproblems. If we draw the tree and we calculate height, it becomes log n. Therefore time complexity of quicksort is log n. In this way quicksort works. Thank you.